Welcome in, everyone. In this video, I'm going to go over relations and functions. First, I'm going to start out talking about relations, domains, and ranges. Then we're going to make the distinction between what a relation is and what is a function. From there, we will go on to tell whether or not it is a function given certain circumstances, like from an equation or from a graph. And then at the end, we will go over function notation and evaluating functions. Let's get into it. To begin this lesson, I'm going to go over what a relation is in terms of a domain and range. So you can see the domain is the set of all allowable x values for a relation. A range is the set of all y values for a relation. And a relation is simply just a set of ordered pairs x comma y. We would say that this is a relation in x and y. On this slide, we are given a relation. You can tell it is just a set of ordered pairs. We have x in the first coordinate for all of these and y in the second coordinate for all of these ordered pairs. What we are going to do is we are going to go ahead and list out the domain and range for this relation. And how we do that is with this relation, we will go through, since the domain is all of the x values, we'll go through and find all of the x values in these ordered pairs, and then we will just write them down in a set 2, 7, 3, -10. There we go. That is the set of all x values in this relation. And I want to point out, you notice that there are two elements that are the same. We only need to write it once. And we do the same thing for the y values, aka the range. So here, a similar idea. We only have to write out the numbers we see once. So I see 3, 0, and -9. Even though -9 showed up 3 times, we only need to write it once. And these elements in the domain and range do not need to be written in ascending order. They can be written in any order. What is a function? I've got a very mathy definition here for you. Given a relation in x and y, we can say y is a function of x if, for each value of x in the domain, there is exactly one value of y in the range. And these are referring to ordered pairs of x's and y's. And if you ask most students of math, do you remember this definition for function? They'll probably meet you with a pretty swift no. What students end up remembering is no repeating x values. And that's just because it makes more sense and is easier to remember than all of this mathy definition up here. Is it a function? On this slide, we are given a set of ordered pairs, and we're simply just going to ask, is this set of ordered pairs a function? All we have to do is figure out what are the x values. So let's go ahead and highlight those x values. And then all we have to do is figure out, do any of those x values repeat? And you can pretty easily tell -3, 19, pi, and -11. None of those values repeat. So no repeating values, which means this is a function. All right, now that we have seen a set of ordered pairs, what I would like to do is also extend that over into a mapping diagram and a table. Table first. So this is what a table looks like. You have the x column on the left, you have the y column on the right, And essentially what we're doing is we're going to be writing all of the elements of the domain with all of their corresponding elements of the range, so that when you look across a row, you'll see an ordered pair that was up here in this set of ordered pairs. So we have -3, 5, 19, 0, pi, comma, -1, and -11, comma, -2. So again, each row here represents an ordered pair, and you can tell just by going down the domain side here, there are no repeating x's. So this is still a function. Let's take a look at mapping diagrams, which are also known as maps. And you can see here we've got two bubbles that represent each part of a function that we're dealing with. We will have a domain bubble and we will have a range bubble. So in the first bubble, we'll have -3, 19, pi, and -1. And in the range bubble, let's start with 0, let's go to -2, let's say 5, and -1. I meant -11 over here. Now, yes, you can put these x values and these y values in any order in the bubble. But we can still match them up by using arrows. So I can match up the -3 with the 5, the 19 with the 0, the 11 with the -2, and the pi with the -1. Now again, since we're using arrows to match x coordinates with y coordinates, any x coordinate that has two or more arrows coming from it would make it not a function. One final thing about maps here is that occasionally, I don't know how often I've seen this, but they could be labeled. Maybe you label this bubble x and this bubble y. But if they are not labeled x and y, what you can do is figure out which one is x and which one is y, simply by finding out where the arrows are coming from and where they are pointing to. Arrows come from x's and point to y's. Okay, one more example. We will take a look here. Is this a function? You might notice that the notation is getting a little odd, and that's okay. Run with it. So I've got a -3, I've got a smiley face, I've got a me, and I've got a me in the first position, or in the x position. This does not represent a function, so we would write not a function, because there is a repeating value in the x position here, in the x coordinate. All right, so what does this look like as a table? Well, we just follow the same process from the last slide. So this is what the table would look like. All of the domain elements in the first column, all of the range elements in the second column, and yes, each row here still represents an ordered pair. But you can still see the repetition of this x value, me. So again, this table does not represent a function. And lastly, for the mapping diagrams, we can only write the domain element once, and we can only write the range element once. We don't need to write me twice here, and we don't need to write -2 twice here. Here's why. When we draw our arrows from -3 to -2 to show this ordered pair here, we can draw another arrow from smiley face to 0 to show this ordered pair here. The next ordered pair we get is from me to 1. No problem, we see that ordered pair here and here. But we do have a fourth ordered pair in the set of ordered pairs, which means we need a fourth arrow. And this fourth arrow is the one that makes it not a function. So there it is. We do have a me comma -2, a me comma -2. And since this x value has two different y values associated with it, that makes this mapping diagram a visual representation of this, which is still not a function. For the second topic in Is It a Function?, we'll take a look at equations. Is y squared, or the absolute value of y, in the equation? That's what you have to answer. If the answer is yes, then the equation you're looking at is not a function. If the answer is no, then the equation you're looking at is a function. I really wish there were more I could explain at this time, but it doesn't make sense this early in an algebra sequence. Is it a function? In this slide, we're going to go ahead and look at the graphs and then tell whether or not what we're looking at is a function. And the way we're going to do that is we're going to use the vertical line test. Now you might remember that vertical lines are represented by the equation x equaling some number. So what that means is if we have a vertical line passing through a graph more than once, like this one here, that means a single x value, maybe 1 as you can see here, will have two different y values, which means if we estimate here, we can say x equals 1 is paired up with y equaling, maybe that's 2.8, as well as a second value of y equaling -2.8, which means we have repeating x's. As you can see here, we have a 1 and a 1. So this particular graph does not represent a function because a vertical line hits it more than once. Now, if you take a look at this graph down here, no matter where we put a vertical line, you can tell that no vertical line will ever cross the graph more than once. And I like to notate this by just maybe drawing some dots. That's where one line hits, here's where another line hits. And then I've got to move down a little bit, it looks like. So we'll do that one, that one, that one, and that one. But each of these vertical lines only passes through the graph once. So this one we would say is a function, while this circle up here is not a function. And lastly, we have this graph over here, which I'm going to make a little bit larger. And yes, I realize this is running off the edge of the screen, but that's okay. The important part to note here is that we have a bunch of little horizontal lines sort of jumping up at a specific value. So we travel to the right here and we jump up. We travel to the right here and we jump up, so on and so on. With this particular function, we call this the step function. Okay. And if we pass vertical lines through it, you can see that it will be a function as well, as each vertical line only intersects the red graph at one point. But what happens if we take a vertical line and we use it at the end point of one of these jumps, maybe this one right here? So pretend this lines up with this endpoint here and this open endpoint here. What ends up happening is the vertical line will only touch the closed endpoint. And you see how this endpoint is open? It's kind of like we can thread the needle with that vertical line and it would just go through that open dot. So even if we line this up very perfectly, let's see if I can do this. There we go. This line only touches the graph one time, and that is at this closed dot on the left-hand side of this step. And like I said, you have to think of it like it is a hole here, and we're threading the blue line through that hole. Now, what happens if we fill in one of these dots, like over here? Then this graph becomes not a function, because what happens then is this vertical line will hit this step at the closed dot and this step at the closed dot, and then it is hitting different y values for the same x value. All right, we're going to switch over to function evaluation now. And the first place we're going to do this is from graphs. So essentially what's going to happen with function evaluation is that you need to remember that f of x equals y. And if we break this down a little bit, you can tell that this very well correlates to an ordered pair. So if I wanted to, I could name this ordered pair right here. I could name it f of -1 equals 1.5, because this ordered pair right here would be -1, 1.5. So we can just rewrite ordered pairs in function notation. That being said, we want to find the following: f of 0. So effectively what we're trying to do is we're trying to find a matching y value that would be paired up with the x value of 0. So as we travel along this graph from left to right, I can see this point right here has an x value of -3, this point right here has an x value of -2, and we're just going to stop tracing along the graph when we get to a point that has an x value of 0 right here. So what we can do then is we can identify what are the coordinates of this point on the graph. It would be 0, 3. So that's the ordered pair, which means f of 0 would just be equal to 3. Now, we can also work backward. We don't have to give you an x value and ask you for the y. You could be given the y value and asked for the x. Let's say 0. So now what's happening is we have an x coordinate that we don't know, but we know the y coordinate here is 0. So I'm just going to do the same thing. I'm going to travel all the way across the graph, as far left as I can start right here at the arrow, and I'm going to stop when the y value is 0. So you can see here, this point right here has a y value of -2. This point right here has a y value of -1. This point right here has a y value of 0. So what is the x value here? Well, x here is -2. When y is 0, x is -2. So our answer would look something like this. X would be -2. But what's different about searching for x values is that we have to keep moving along the graph to here, because this is another x value that has a y value of 0. This ordered pair is 2, 0. So we also have to include that as well. And we would travel around looking for all of them, but there was only going to be one y value for this x of 0 because this is in fact a function and passes the vertical line test. And very similarly, we could do the same thing here. So with this particular graph, we want to find f of 3. So we know this is an x value because it's in that set of parentheses with the function name next to it. So 3 would come down here to our ordered pair. So we just have to stop whenever we find the ordered pair, the point on the graph here with an x value of 3. So this one's -4, we can keep traveling, -3 x value, -2, -1, 0, 1, 2, and 3. There's the x value 3, I'm going to stop. The y value associated with that is 2. So we can substitute a 2 here, which means f of 3 equals 2. We just need that number answer. And the same thing down here, we could ask something like this. Find f of x, find an x value so that the y value is 3. So if we're trying to find an x value, again, I'm just going to travel along this graph from left to right until I find a y value of 3. You can see the associated ordered pair here will be something, 3. We don't know what that something is yet, so travel along until you get to a height of 3. And that x value we can estimate to be about 4.5. But that is how you evaluate a function from a graph. And yes, we should not be trying to trick you from this because it is called function evaluation. So all of the graphs you look at should be functions. All right, we're going to move on to a set of ordered pairs. So we're going to do the same thing. Just notice that we have some ordered pairs here in a set, and these could be represented as a table or a mapping diagram as well. And you should still be able to answer these questions. And I have to very briefly make this change here, make it f. So f is a function and it equals this. So you don't even have to look, I promise this is a function. Okay, so f of -8 means we're just trying to find the ordered pair up here with an x value of -8. That's this one right here. And just report back what's the corresponding y value with that. And it is -pi. And we're going to do the same thing for the next one. f of 19. Are there any? Yep, here it is. Let's keep checking. Okay. Are there any ordered pairs with an x value of 19? It's right here. So then we just look at the corresponding y value. It's -2. Now this one I throw in here just for funsies. f of 0. If this is all of the information we have, we're not looking at the graph of this or anything, just a bunch of ordered pairs. We're trying to find an ordered pair with an x coordinate of 0. There aren't any. So what we would say is this is undefined because there aren't any ordered pairs with an x coordinate 0. Now, I assume it could be done in reverse, but I don't go over that in this video. But we can also break this down into, as I mentioned, going in reverse. If we know f of x equals 15, then we need to find an x value that corresponds to a y value of 15. And you can tell we're looking for an x value because there's an x there. So let's take a look at the y values. No. Okay, here it is. The y value of 15 is paired up with the x value 13. So we would say x equals -13. And finally, here we have a y value of 5. Looks like we have 2 answers. Is that right? Are we allowed to have 2 answers here? So we have x equals -3 and x equaling 5. Is that right? We can't have repeating x's. Well, if you take a look back over here, no x's still are repeating because one is negative 3 comma 5 and one is negative 5 comma 5. Repeating y values, a-okay. All right, last topic for this video, function evaluation. Equations. We're going to take a look at the function equations. And I'm going to hopefully make this as understandable as possible. Function evaluations with equations is all about correctly substituting values. What does that look like? Well, as you've seen with the previous two evaluation slides, it's always been about correctly substituting values. So, for example, we can write underneath this f of x, let's say I replace x with 2. Well, that means on the other side of the equation, we will also replace x with 2. And I want to point out here that I put parentheses around this 2. Very important to help you keep track of your order of operations. But this works with anything. I could substitute negative 5 in for this value, and I would substitute it over here. I could substitute a variable in for this value, and I would put it over here. I could substitute a much larger variable expression. Why not x squared plus 7x? X squared plus 7x. But everything else around it would remain the same. Plus 2. F of h equals 3 times h plus 2. F of this monstrosity equals this 3 times this monstrosity plus 2. And then we would just have to go through and simplify as best we can. So for this first example up here where I substituted 2 in, 3 times 2 is 6, 6 plus 2 is 8. And that's it. We're after that answer. Here, substituting negative 5 in. 3 times negative 5 is negative 15. Negative 15 plus 2 is negative 13. Great. Here, can we even simplify anything here? I replaced x with h everywhere. So 3 times h is just 3h plus 2. This is just 3h plus 2. And this last one, oh, that's going to be a doozy, huh? We can distribute a 3, so we can get 3x squared plus 21x plus 2. Yep, I think that'll do it. Even if you see this and you're thinking to yourself, oh man, that's quadratic. Maybe I can factor that? No, don't worry about it. The only thing we're asking you to do is substitute that in and simplify if needed, like distributing and combining terms. That's it, no need to factor. So for this other example over here, we have g of x, g just being a different name for a function, g of x equals 4 minus x squared. And we can go through and just do all sorts of other things over here. Maybe we can say g of 7, sure. Maybe we can jump right up into doing something like this. G of, let's say 6x squared, not squared, 6x minus 1. And I think for the last one here, I'm going to say g of smiley face. I think smiley face is going to be showing up a lot in these videos. So we can go through and figure these out, right? This is 4 minus something squared. This will also be 4 minus something squared. This will also be 4 minus something squared. That's something that x is changing in every single different evaluation here, though. So this is 7 in parentheses. This is 6x minus 1 in parentheses. And this is smiley face in parentheses. I hope you're picking up on that. You need to have it in parentheses. So what will happen is I'm going to start with this last one. That smiley face is just making me all sorts of happy. We can square the smiley face to just be smiley face squared. Ooh, I've got it. Here's a fun dad pun for everybody out there. There we go. This is not real math happening. I'm just having fun now. So maybe this would be the correct answer here. All right, so maybe we can jump back up here to this one, 4 minus 7 squared. Well, we need to work through the exponent first, as the order of operations says. So 4 minus 49 would be negative 45. Okay, then with this one in the middle, we're going to have to do a little bit of work. So yes, we're going to square that 6x minus 1, but it's going to look something like this. 6x minus 1, 6x minus 1. And we need to take care of that multiplication first. So 6x minus 1 times a 6x minus 1 will give you something like this. 36x squared minus 12x plus 1, still in parentheses because of this negative sign. So we're going to distribute this negative to each term in the set of parentheses. What does that become? Negative 36x squared plus 12x minus 1. So let's see, 4 minus 36x squared plus 12x minus 1. And then from there, we can actually combine these two here to get finally negative 36x squared plus 12x plus 3. And I know I'm really squeezing that in there, but this would be the simplified answer for that. And I think that's it for this video. I really hope this video helps you out. Good luck.